Okay, this lesson is how we're going to do some calculations on our spur gear project. So each of you will be assigned a specific spur gear to cut. They are all 2 inches or smaller diameter. You'll have a handout like this to tell you all the information you need, but we're going to walk through this pretty quick here. Let me pull this down just a bit. Okay, these are typical spur gears right here. That's spur gear, spur gear, spur gear. So it's just basically a gear that looks like this. Modern machining, they just have a gear cutting machine. They throw it in the machine and cut the gear. We're not so fortunate to have a $500,000 machine to do that. But we're going to do it the old-fashioned way, where we're going to learn how to heat treat, how to do some calculations, and use an indexing head. Okay, so there is basically our gear. It looks kind of like what we do on the arbor press. Okay, so let's look at the parts of the gear here, and I'm going to show you some of the things that we need. The addendum, we need that. We need the outside diameter, working depth of the tooth, hole depth of the tooth, and the tooth thickness. And we'll talk a little bit more about each of these as we get into it. So in Blackboard, you have this PowerPoint, and it has all of this for you. Okay, so you notice that nothing's highlighted blue here, so I really don't care about these formulas here. Anything that's highlighted light blue, I want to know what that is. So outside diameter, I've got to know the diameter I'm going to cut my blank to, because remember, you're going to make a blank that looks kind of like this. It's just 1 inch wide, 2 inches or smaller diameter, with a 1 inch hole in the middle with a chamfer on each side. Okay, but how do you know that outside diameter? Well, the number of teeth plus 2 divided by your diametrical pitch will equal your outside diameter. The number of teeth is given to you, the diametrical pitch is given to you, so you should be able to calculate your outside diameter. But fortunately, on this handout that I have here, it has all of that information for you. But I believe there are some quizzes online that you'll have to do to calculate that anyway. Now, your hole depth, how deep do you cut the teeth into this thing? Well, if you take the constant 2.157 divided by the diametrical pitch, which we give you, you'll be able to calculate the hole depth of the tooth. So when you're cutting those teeth on the vertical milling machine, you'll know how deep to cut. Also, the addendum. What is the addendum? The addendum is about halfway down on the tooth. If we can see a tooth about halfway down, we use that measurement or that number. We use that for measurement only. That's not for making the gear or anything. This is only used for measuring once we get done. So we just take 1 divided by the diametrical pitch, and that will tell us the addendum, okay? Tooth thickness. How thick is this tooth at the addendum point? And this probably doesn't make sense now, but it will hopefully in a few minutes. We take this constant number, 1.5708 divided by the diametrical pitch, and that will give us the tooth thickness at the addendum, halfway down. Don't need that. Pitch diameter, there's some various pictures of teeth. Now, if you notice this cutter right here, this is a typical cutter. Diametrical pitch is given to you, 12. The pressure angle on all of our cutters are 12.5. Some of the modern cutters are different. Modern gears are a little different, but all of ours are 14.5. It's a number 6 cutter. Now, I do have a nice handout for you here. It's in your folder, and it tells each cutter number what range of teeth it will cut. So if I have a number 6 cutter, according to my handout, I can cut 17 to 20 teeth. 17 to 20. See that? It's a diametrical pitch of 12, 14.5 pressure angle, a number 6 cutter. Number 6 cutter cuts 17 to 20, 17 to 20. So you're going to need that information. Okay, so here you go. Number 6 cutter, 17 to 20. Now, if you happen to select a gear to cut that has 24 teeth, you're going to take a cutter that's a number 5 cutter. So we're kind of limited on the cutters that we have. They're very expensive, they're getting harder to find. So we only have about 20 or so cutters. Some are better than others. So once you pick your gear, then you'll want to make sure you find a cutter for that. All right. So here's some of the information we need. We need the diameter of the gear. So here we're taking an example. We're going to cut 40 teeth on a 10 diametrical pitch gear. And this is just an example. So I need to know the diameter of the gear. What's the outside diameter of this gear? So I would take the number of teeth, 40 plus 2, it's always plus 2. 40 plus 2 divided by the diametrical pitch of 10, 42 over 10, divide it, and it gives you 4.2. Okay, so that would be quite a bit bigger gear, but this is just an example. And the depth of cut, I would take my constant, 2.157, divided by the diametrical pitch of 10, and there's my depth of cut, 216. The addendum is what we need to measure. It has nothing to do with making the gear. I just take 1 divided by 10, diametrical pitch, and it gives me 100 thousandths. And then I want to know the tooth thickness at the addendum. Okay, so I'm going to show you this in just a minute. So it's 1.5708 divided by the diametrical pitch of 10, gives us 157 thousandths. Okay, so for 40 teeth, if I were going to cut that 40 tooth 10 diametrical pitch gear, I would select a number 3 cutter that goes from 35 to 54 teeth. All right, now I think I want to back up. Let me back up just a minute and I want to show you this. Let me show you from right here. This is a pretty good picture. Let me show you this. So when I talk about the addendum and the tooth width, you notice how the gear has a 14.5 degree pressure angle? Well, when I measure down from there to there, that's the addendum. And then I want to measure the width at that point. And that's my tooth width, or the thickness. Okay? So you notice how the teeth are different thicknesses all over the place. So I can't just measure the thickness at any point. I have to be at a certain depth to measure that thickness across there. And then what we usually use, we have a neat little gauge. It's a gear tooth gauge, which it was veneer. I changed it, added some digital indicators to it. So now we can set this indicator at the addendum, and then we can measure the width at that point. Okay, so what it does, we can set the addendum here vertically, and that moves this plate up and down. And then we can measure with the horizontal indicator the tooth thickness. Okay, so let's take off back where we were. Okay. The machine's going to be set up kind of like this. It's going to have an indexing head, a center on the indexing head, or a chuck. Depends on which indexing head we have. We have some of each. You're going to have your gear blank here. You're going to have your mandrel pressed into it like that. Then you're going to have a footstock at the other end to hold this. Now it's real critical to run an indicator across the top and across the side to make sure our mandrel is not tilted or in and out. We don't want any variation there either. Now the only difference in this picture is this is a horizontal mill. The cutter is running horizontally like this. We're going to have the cutter like this. Remember, you're going to make this arbor, you're going to have this cutter, and you're going to cut this gear like this. You're going to cut the teeth, you'll index it, you'll cut a tooth, you'll index it and cut a tooth until you're done. And we'll go in a little further about that on how to do that. Okay, so, and again, this is a horizontal mill. It's a little bit different, but I'm actually going to set one up on a machine, videotape that, and that way I can show you how we actually set it up on the machine. Okay, so we're going to cut the depth, whatever depth we have. If it's 157 thousandths or 210 thousandths, say if it's 210 thousandths tooth depth, the depth of the tooth, the total depth, we would actually, in the first pass, we're going to cut it 210 minus 40. So we would cut it at 170 thousandths deep the first pass. So here's our cutter, arbor. It's going to cut like this, but it's going to be 40 thousandths shy. We'll cut each tooth. We'll go along and cut each tooth. Then the last pass, we'll move it in that last 40 and clean it up. And then we'll have to go around again and cut the teeth again. So it's kind of a slow process. Takes a couple hours to cut the teeth. But the first pass all the way around each tooth is going to be the total depth minus 40. Here you see an example, 216 depth minus the 40. You take it 176 first pass all the way around. Last pass, 40 thousandths to clean it up. You want to use plenty of oil as well. Okay, most of this I'm going to show you at the machines. There you can see how we're going to measure this. Remember, vertically we're going to set this from here to here is the addendum. The addendum is set for every specific gear. So the vertical scale on our gauge, like this, here's our gauge, it's going to be set at the addendum, whatever it may be. If it's 157, whatever, we'll set this vertical scale at 157. Then we'll take and we'll measure the tooth width at that point, and that will give us our measurement, okay? So you can see right there, there's the addendum, it's top of the tooth to a certain distance, and then the distance from here to here is going to be our tooth width or thickness. Okay, the next video we'll look at on how to use the indexing head, which is very complicated, but once you learn it, nothing to it. You won't have any problems. All right, in this video, we're going to look at how to set up and operate the indexing head that is mounted on our Acra vertical mill. Typically, they're on a horizontal mill, but we have ours set up on a vertical mill. It's the indexing head that you probably use to put the hex on the center bolt of your tool post, to put a square on your key seat shaft, things like that. But we're going to use it to cut teeth on our spur gear. Okay, so this PowerPoint is on Blackboard. So if you want to go back and review it, that's great. There'll probably be a quiz with it. So let's look at the typical indexing head. There's the indexing head. There's the footstock. It's set up on the milling machine table. There you can see the plate with the crank, and they'll have two sector arms on it, which all of this I'm going to demonstrate at the machine. So I think that'll help when you actually see someone else do it. Okay, so simple indexing, that's what we're going to be doing. So that's where we're going to be using our plates. We're going to be doing some mathematical formulas to calculate how many rounds we need to turn for each tooth, because it's not as simple as making a hex. Okay, so here's our plates, there's our sector arms, there's our crank. And again, I'll show you how to use this when we're at the machine. So there are 3 plates available to choose from. And out of these plates, you can make any infinite number of teeth on a gear. The first plate, this plate right here, it has holes 15 to 20. The second plate will have 21, 23. You notice it skips a lot. That's okay, because we can go back and use that one if necessary. And it goes 21 to 33. The next plate, the fine plate, number 3, it goes 37 to 49. So we will be using these plates based upon which gear you're cutting, the number of teeth you're cutting. And also, this is on a handout that I made for you. It has the gear cutters, and it also has the indexing head plates. All right, now here's the formula you'll use to calculate. And our biggest calculation, we want to know how many cranks, how many rotations to make one tooth. So as we rotate this indexing plate, the crank on this indexing plate, it's going to rotate this gear to the next tooth. But it's not as simple as just 1 turn or 2 turns. It's going to be 1 turn and a fraction, 2 turns and a fraction. So the formula that we use is 40 divided by the number of teeth. That's the formula we're going to use to calculate how many rotations for each tooth. Here's an example. This one's pretty simple. So if we had 8 teeth or 8 sides, an octagon, we would just simply rotate it 5 turns. But it's not going to be that easy for you because you're cutting a gear with more teeth. Here's one with 5 sides or 5 teeth, it would be 8 turns. Again, very simple. We're not going to do that. Ours are going to be harder. So say if you have 30 teeth, you're going to cut a gear. It's going to have 30 teeth, 30 equally spaced teeth. We would take 40 divided by 30. It's going to give us 1 and 10 30s left over, correct? And make sure you put this 30 here. Some people want to put this 40 over here. No, we're not concerned about the 40. 40 divided by 30 is going to be 1 total rotation, and then 10 over 30. We want to reduce that fraction as low as we can, reduce it down to 5/15, eventually down to 1 1/3. Okay? So we would rotate for each tooth, 1 rotation and then 1/3. But how much is 1/3? That's what we have to think about. Okay? So we're going to have to find something that the denominator will go into equally. The denominator is the bottom number, the 3. So we have 1 rotation and 1/3. Well, which plate do we use for this? Well, I look at my plates and I see the plate here has a 15 hoe series. So I could use that one. It's got to be divisible by this 3. Okay? So if I use this plate, it has a series of hoes with 15 hoes in it. So I could go 1 1/3 can be multiplied by 5 on each of those. So it would come out to 1 and 5/15. So I would rotate 1 complete round on this inner circle, 1 complete round, and then 5 spaces on the 15 hoe pattern. All right. And again, I'm going to show you at the machine, so we're kind of building upon what we're doing here. All right, so it would be 1 complete rotation and then 5 spaces on a 15 hoe plate for each tooth. All right. Now let's look at another one, 25. Now I have 25 teeth on this one. So the formula is still 40, constant number 40, divided by the number of teeth. It comes out to be 1 and 15 25s. Well, when I reduce that enough, it comes down to 1 and 3/5. So I need a plate that's divisible by 5, okay? And what I'm going to do, I'm going to look again at this plate here, and let's see, it has 20. It has a series of hoes with 20 hoes. So I could go 1 rotation and 12 spaces on this 20 hoe ring here. 1 complete rotation and then another 12 spaces, not hoes, spaces, 12 spaces on the 20 hoe pattern here. All right? So it's very critical that we know how to do this. And there's some practice problems on Blackboard. I think there's a quiz, and that'll help you kind of understand this a little bit better. So to make a 25 tooth gear, we would rotate the indexing head, 1 complete rotation and then 3/5. But we've got to have a series of hoes that's divisible by 5, so we chose the 20. We could have chose 15, but we chose the 20. And then 5 times 4 is 20, 3 times 4 is 12. That's where these numbers come from. Whatever you do to the denominator, you have to do to the numerator. Remember your math. Okay, so we would go 1 complete rotation and then 12 spaces on a 20 hoe plate. Here's one here with 18 teeth. So I would take 40 divided by 18 would be 2 and 4 18s left. So the 4 18s would reduce down to 2 9s. So I have to have a plate with a series of hoes that's divisible by 9. So on this plate here, I have a set of hoes, 18 hoes in it. This is plate number 1. It goes 15, 16, 17, 18, 19, 20. So I could go 2 complete rotations, and then I would go 4 spaces on the 18 hoe plate. That's for each tooth. So to make an 18 tooth gear, I would rotate the crank for each tooth, 2 complete rotations, and then 2 ninths of another rotation. But using this plate with 18 hoes in it, I would go 4 spaces on the 18 hoe plate. Remember what you do to the denominator. 9 times 2 is 18, 2 times 2 is 4. That's where I get that 418 from. This is what the 40 divided by the 40 divided by 18 is here, but I've got to find out what plate it fits. All right. So that's how we do this. This is how we calculate it. It's 40 divided by how many teeth you have. That'll tell us how many rotations we need. And it's always going to be a rotation, 1 or 2 rotations, and then a fraction of a rotation. But that fraction of a rotation is what we have to use these hoses for, okay? So we'll do a demonstration at the milling machine next and see what happens. So again, I hope this helps. Again, there's some questions and practice problems on Blackboard that will help us through this. Thank you.